He was the president of D-Wave International, the world's first commercial quantum computing company. Now he's the CEO of Cold Quanta, so he's on his second quantum company. He was appointed by the White House to the President's Information Technology Advisory Council by Presidents Clinton and Bush. Please welcome to the stage Mr. Bo Ewald.
Whoa, quantum pyro, cool. So I'm really pleased. This is the first time I've ever been to Bulgaria. I'm really pleased to be here because you may not know this, but Bulgaria is kind of the father of modern digital computing. The first digital computer, first automatic digital computer, was invented by a man named John Atanasoff and others at Iowa State, and his father, And his father, Ivan, was born here and emigrated to the United States, electrical engineer, and then his son did that. So I'm a kind of a history buff as well, so it's great to be here. And we're going to give you a quick introduction to things quantum, probably, and we'll do that very quickly. So really pleased to be here, and quantum computing will take years to understand, more years to be able to be put into practice, but we'll give you a quick introduction to it, and also to other things quantum that you might actually see that will affect your lives about the same time quantum computing will. So we'll talk a little bit about quantum terms, and then just quickly highlight some of the other applications of things quantum, and then quantum computing early applications, and I think we might see 2 or 3 quantum computing applications in production before the end of the year this year for small problems. Okay, you can have all of these slides if you would like, however we arrange that. I have a collection of things with the presentations and things at the end to point you toward the application areas. But what quantum really means is discrete, quantized. And so it's not a big mystery, but the way it works is a mystery. Quantum is also probabilistic. So that means we aren't, as in digital computing, where we're certain a bit is a 0 or a 1. In quantum computing, it's going, at the end of the calculation, it's probably going to be a 0 or a 1. We'll turn it into a digital state, and it will become one of those. The big 3 words that you'll hear over and over and over again, particularly in quantum computing, are entanglement, superposition, and quantum tunneling. So what entanglement means is if we're lucky enough to get our quantum bits, called qubits, lucky enough to get them entangled, then we can sort of make coordinated moves with them or communicate between them without actually sending any communication signal as we know it today between them. So that's entanglement. Think of it as getting your fingers entangled and being able to move in a coordinated space. Superposition, our quantum bits or qubits start off in a state of superposition where they're both a 0 and a 1 simultaneously. And then through the extent of the calculation, at the end of the calculation, we measure them. And when we measure them, we take them out of the quantum state, and that forces them to become like a digital bit, so they become a 0 or a 1. Quantum tunneling really means that the world of quantum is kind of like a cat, and it wants to go to a low energy state, that nature wants to do that, and we won't talk about that more now. But the time factor in things quantum is called coherence. That's how long we can keep our system in a quantum state, and then decoherence is when it falls out. That's really important. We're relatively short periods of coherence today, and that's a big challenge for us working in quantum computing. So you'll hear those terms throughout, and the next slide. The next slide is one that I borrowed from a general in the United States Air Force. He gave a great presentation saying these are things that we see happening in quantum in the United States Air Force and its civilian analogs. So what he's saying is over the next 5 to 10 years or so, they'll not only see quantum computing being in play, but also quantum communications, quantum networking, quantum sensing, as well as then quantum computing. And so what those enable, What those things will enable are shown on this chart. So basically, we'll have a whole new set of instruments and components that are doing things quantum. In fact, our new company has, we have a device that's working on the International Space Station as we speak right now. It's creating what's called a Bose-Einstein condensate, which is sort of a different form of matter than those that we're used to. And it's been fired on a rocket installed by astronauts in the space station and is working 24 hours a day, basically for scientific experiments. So you'll see a collection of things like that. You'll also see what I call a quantum positioning system being able to be developed. That'll take a while, but with quantum devices, we're going to be able to create better timing, and then we're going to be able to very accurately know what the position is, what our position is anywhere really in the galaxy. And so over time, we won't have to use the GPS satellites to know where we are and what time it is. We'll be able to use devices that will start off being, fairly large, but over time, you'll probably have one in your cell phone, and you won't have to communicate with satellites to know exactly where you are. And on the communication side, quantum communication will also enable us to send communication without it being able to be read by others, or they may know we've sent a communication, but they won't be able to read it. And then finally, quantum sensing may take the longest period of time, but we believe that with quantum technologies, we'll be able to design better radars, better sensors for airport scanners, for example, and eventually, because of some of the inherent advantages of things quantum, probably better devices to be able to look at biological samples like you and me, and probably get more accurate readings than we can with NMR machines and other things like that. So it's a long way of saying, stay tuned. There's a lot of quantum stuff coming, and it's going to be part of your lives, and it won't just be computing. If you want a little more background, there was just an article in Science magazine about 2 weeks ago by 3 of the fellows who've been helpful on creating the National Quantum Initiative in the U.S. There's also the European Quantum Flagship Program going on, about the same size we expect. And then in the U.K., there's the Quantum Hubs program going on, and then a big program announced in China. So many, many big international quantum efforts going on. The U.S. one was described there. I went too quickly. The previous slide, if we could get to it, was the first time I ever heard of things quantum. I used to run computing at Los Alamos a long, long time ago, and it was the 40th anniversary of the Los Alamos National Lab in the U.S., and I ran the computing division there, and they had a celebration for the 40th anniversary of the founding of Los Alamos. And there at 9 o'clock on the first day of that meeting in 1983 was a talk by Richard Feynman, Nobel laureate, as are most of the other people on that list. And it was a talk entitled, "Tiny Computers Obeying Quantum Mechanical Laws." I'd never heard of quantum computers before. And a couple of days later, I was taking Feynman and other Nobel laureates, Edward Teller and a whole collection, Bloch, and I think Hans Bethe was still alive then, taking them on a tour of computing at Los Alamos. It was the largest computing facility in the world at the time. And I said, and this Cray supercomputer behind me can do about 160 million calculations a second. And Feynman said, young man, someday all of those big Crays are going to be replaced by quantum computers. And the first time I talked to this Nobel laureate, I said something like, wow, or cool. It took 35 years, but 35 years later, Los Alamos bought their first quantum computer. So it's been a long time coming, and the result of all that now is that when you design a quantum computer, you design it in the same way or in a similar manner as you would with a digital computer. Basically, what we have to do with digital computing and quantum computing is marry a technology with a system architecture. So on the technology side, this is an article from Science magazine again a couple of years ago, and it shows the different types of qubits that you could use, the different types of technologies you could use to implement a quantum computer. Most of us have used superconducting qubits so far, and I'll show you what one of those looks like. Ion traps are coming along. In fact, Honeywell, just the CEO of Honeywell yesterday just announced that they're working on an ion trap quantum computer, and Microsoft is working on topological quantum computers. This article was just written 2 years ago, and even since it was written, there are two new technologies. One is called cold or neutral atoms. That's what we're working on at Cold Quanta. And the other is a photonic approach, and there's a new company in Silicon Valley called PsiQuantum that's working on that approach. So even though it's been around for a long time, we're really just at the beginning of the race toward quantum computing. So those are different technologies you could use to implement it. Two different architectures, two big architectures are in use. IBM and some of the other companies are using what we call a gate model architecture, and the other architecture is called quantum annealing. We'll look at both real quickly. This is the IBM Q System 1. They just announced it officially at the Consumer Electronics Show in Las Vegas earlier this year. It's one of the coolest things you'd ever see, and at the heart of it is a big cylinder kind of in the middle, encased in a lot of glass and shiny things. The way it works, this is from our friends at the German National Laboratory at Jülich. Those horizontal lines are qubits, and on those qubits, you put gates, much like someone has you in a digital computer, a computer designer has connected a series of gates. Well, you become the designer, and you apply gates to those qubits. The qubits start off with a value, and the gates connect the qubits and perform the calculation. And at the end, you force the machine out of a quantum state, and each of those qubit lines becomes a 0 or a 1, and that's your answer. So gate model quantum computers are sort of like the digital computers we've had, except they operate because they use gates, but quite different approach to thinking about how to program them. The other approach that we use is the quantum annealing, and this is like sort of a diagram of how to think about the D-wave quantum annealing computer. If you had a mountainous landscape, what the D-wave quantum annealing computer does is, using those quantum techniques, it finds the lowest valley or valleys in that landscape, probably. Not guaranteed that you get the best answer, but it probably does. And it doesn't do it in any way that you could relate to from a digital computing background. So think of it as finding a low valley. This is what two of those machines look like, and they're about 3 meters by 3 meters by 3 meters high. If we opened the door and walked inside, you would see a big soup can. And if we took that off, it's a shield. If we took that off, there's another one inside and another one and another one. And if we took them all off, you see sort of the Terminator's arm. And right down at the very bottom of the arm is one chip, and that's the actual quantum computer. And there it is. And this is one from the current D-Wave machine, and this one has 2,000 qubits, over 2,048 qubits. And it's a regular chip. It's about the size of your thumbnail. So all of that big box and shielding and things are to keep the machine in a quantum state. The machine is about the size of your thumbnail. Now, what can you do with it? Well, optimization, because it's finding a low valley, that sounds a lot like an optimization problem. People have also applied it to machine learning, material science, and cybersecurity. And I'll give you references at the end, which have about 100 different early applications. But of those 100 early applications that D-Wave customers have done on the machine, about half are optimization, about 20% machine learning, and then a collection of other things. The machines are installed at, these are roughly $10 million supercomputers. Lockheed Martin in the US, Google purchased one, Los Alamos has one, and then Oak Ridge National Lab in the US uses about 20% of one. And then there are a large now collection of cloud customers. They're up to about 100 paying customers on D-Wave machines today, and you can see them here. The thing I wanted to point out is that toward the end of the year this year, I think we may see some smallish production applications of quantum computing. And the first one I would highlight is from Recruit Communication in Japan. They have the leading hotel recommendation service in Japan. They've been able to get better business results by providing recommendations using the optimizer on the D-Wave machine than they did with their normal technique. My friend Martin Hoffman, who's the CIO of Volkswagen, at another one of these big conferences in Lisbon, has said that this year, if you visit the Web Summit in Lisbon in, I think it's November or December, and you want to go from point A to point B, that he will provide, that Volkswagen will provide on your cell phone, an optimized routing for how to get from where you are to where you want to go. Should you take a taxi, bus? If you're driving, what's the best route to go? And then thirdly, our friends at Denso, the big Japanese car components and other components manufacturer, has made some videos that you can use where they've automated the flow of robots in their factories and in fact have been able to minimize the congestion of those robots by about 15%, and they're now saying that they're going to implement that same technique in all of their production factories around the world. You'll see that in the videos that they've made. So long list of websites here with lots of presentations if you're interested in more detail. Things quantum are coming. They're going to be part of your life. There'll be instruments and computers and sensors and communication, and there's one flying right now on the International Space Station. Thanks very much.